Section 3.8, Rates of Change in the Natural and Social Sciences. We know that if y equals f of x, then a derivative dy divided by dx can be interpreted as the rate of change of y with respect to x. In this section, we examine some of the applications of this idea to physics, chemistry, biology, economics, and other sciences. Let's recall that from section 2.6, the basic idea behind rates of change. If x changes from x1 to x2, as we can see in the graph here, then a change in x is going to be the following. Change of x is going to equal x2 minus x1. And the corresponding change in y is f of x2 minus f of x1. And therefore the difference quotient would be the change in y over the change in x, which is equal to f of x2 minus f of x1 over x2 minus x1. And this is the average rate of change of y with respect to x over the interval from x1 to x2, and can be interpreted as the slope of the secant line PQ in Figure 1. Its limit as the change of x approaches 0 is the derivative f prime of x1, which can therefore be interpreted as the instantaneous rate of change of y with respect to x, or the slope of the tangent line at p x1 of f of x1. Using Leibniz notation, we write the process in the form dy over dx is equal to the limit as the change in x approaches 0 of the change in y over the change in x. Now, whenever the function y equals f of x has a specific interpretation in one of the sciences, its derivative will have a specific interpretation as a rate of change. As we discussed in section 2.6, the units for dy over dx are the units for y divided by the units for x. We now look at some of these interpretations in the natural and social sciences. For physics, if s is equal to f of t is the position function of a particle that is moving in a straight line, then the change in s divided by the change in t represent the average velocity over a time period change of t, and the velocity v is equal to ds divided by dt represents the instantaneous velocity, the rate of change of displacement with respect to time. The instantaneous acceleration a of t is going to equal the velocity, which is v prime of t, which is equal to the position function, the second derivative of the position function, s double prime of t. This was discussed in section 2.6 and 2.7, but now that we know the differentiation formulas, we are able to solve problems involving the motion of objects more easily.